Heinemann Higher, Chapter 7 in Polynomials, mixed exercise 7k at the end. Question 5. You're given this function here, this cubic function with two unknown coefficients, but a couple of factors. You're given the x minus 1 as a factor, just a note here, and x plus 4 as a factor, which should be sufficient to find p and q, which indeed is part A. Find p and q. Well, if x minus 1 is a factor, then the remainder should be 0 when I put 1 into this synthetic division with these coefficients. I'll just space it out a bit more because I'm carrying these letters across. So I've got add it down, multiply up, add it down, multiply up, add it down, multiply it up, add it down, 7 plus p plus q. So I've got that for the remainder, but I'll now make a statement. X minus 1 is a factor, since I was told that, which means that 7 plus p plus q should equal 0 as remainder. And that gives me one equation. There's an equation with p and q in it. I also know that x plus 4 is a factor. So if I put x plus 4 into that, I'll do that down here. I've got 2, I've got 5, I've got p, I've got q, spacing it out more since I'm going to pick up this p and carry it on, so I'll need no more space, there'll be a couple of terms. And I know that negative 4 should work in it, so add it down, multiply it up, add it down, multiply it up, add it down, multiply it up, so that's negative 48 minus 4p, add it down, negative 48 minus 4p, and of course that should have been plus q at the end as remainder. But if that's a factor, that means that negative 48 minus 4p plus q should equal 0 as a remainder. Call that number 2 as remainder. And there's a second equation. Now I've got two equations and two unknowns, so I should be able to solve it. Multiply that by 4 and the p's can get knocked out. So here's my plan. Number 1 times 4, leave number 2 alone. So number 1 times 4, 28 plus 4p plus 4q equals 0. Second one, leave it alone. Negative 48 minus 4p plus q equals 0. Add them together. And I've got that cancels out, so I've got 5q, and that part equals 0, and that's negative 20 plus 5q is 0. So 5q is equal to 20, so q must equal 4. Substitute it back in. Right. So substituting q equals 4 in the easier one is number 1. Gives me 7 plus p plus 4 equals 0. So p must equal negative 11. And that was the first part. Find the values of p and q. P is negative 11, q is 4. And so part B. Now, cleared it all away. I could have reused that synthetic division, putting those numbers into it, but I'm just going to do the factorisation by inspection this time. Reuse it if you like. Now if that equals 0, that means that expression must be 0. So it's 2x cubed plus 5x squared, and p was negative 11, so minus 11x, and q was 4, so plus 4 should equal 0. Now, without looking back to the synthetic division, I already know two of the factors. So that x minus 1 was a factor, x plus 4 was a factor. That just leaves one remaining linear factor, which you can do by inspection, the same way as you factorise the quadratic that's left. The first times the first times the first must make the first, so I need a 2x, so I've got 2x cubed. The last times the last times the last must make a 4. Well, I've got negative 4 so far. I'd have to multiply by negative 1 to get back to positive 4. And then I get my answers. The answers are going to be, take them in order, negative 4, then the positive 1/2, and then the 1. There, that would be the answer to part B, or the solutions to that equation. Now you could have put your factorised, you could have redrawn your table, I suppose, even, just putting those numbers in, the 2, the 5, the negative 11, the 4, and then put one of those in, like the 1, and just going through it again. 2, 7, 7, negative 4, 0, and then had the x minus 1 times this, which would have factorised to that. But it wasn't necessary because you already knew 2 out of the 3 factors. and you can just do it by inspection. Right, that's question 5.